left, we said that most of the time, almost always, whenever we see a new stuff in computer science, especially with operating systems, most probably we saw that problem before, it happened before. We have seen this with the memory, we have seen this with the CPUs, we have seen this with the programming languages and the secondary storage. So it is important to know what happened in the operating systems of computer science history. Okay, so that was about computer hardware and some operating system concepts. Let's talk more about this operating system concept. One of them is the system calls. The only way to talk to an operating system is to make a system call. Okay, so let's look at what happens when you make a system call. Let's say you all know this. C function read from your C programming classes. Read, this is the file descriptor. You open a file, you get this file descriptor. You provide the buffer, it's an address to a buffer, and you tell the function how many bytes you are going to read. Okay? When you execute this function in your C program, this is what happens. First, you push this number to the stack, then you push this address to the stack, then you push FD to the stack, and you call the read function from the standard library, right? From the standard library of the C language. Standard library, of course, it runs in the user mode, user space. It is not a part of the operating system, it is part of the C programming language. So the standard library starts running, it puts a special code in a register, okay? That code is for the system function read, okay, system service read, and it asks the operating system to execute that read system call, okay? And it traps the kernel. After this time, step number 6, now we are in the kernel mode, okay? Kernel mode is down there. So you call the standard library function read, and it makes the preparation, it puts that the code for the read function in a special register. Açık kalsın orası ya. Aç hadi iyice aç. It puts that number in the register. Then from that on, you trap to the kernel, to the operating system, and operating system starts running. When you come here, when you call the operating system, you trap to the operating system. You are now in the kernel space, okay, or kernel mode. You can do anything you want, but the function is not yours. The function is by the operating system. So you can do what the operating system wants. All you do is you just give the number for the read. You just give the number for the read system call, and when you come here, dispatcher finds the, okay, this is a table. This is a table. In this table you have entries like read, okay, for the read, for the write, for open, for fork, for wait, TID, etc. How many system calls you have, it depends, and you have the addresses, okay? For the read, you have a function pointer. For the write, you have a function pointer, and it points to somewhere, okay? So for read, the dispatcher finds the address for the read function, and the system call handler handles that read routine using those 1, 2, 3 parameters. And when it is done, it returns to the caller, okay? And from the caller, you return to the C program that calls the function read. Then after that, you increment the stack pointer. Why do I increment the stack pointer? Because I don't want to keep these numbers in the stack anymore. I don't want them to stay there. That's why I increment the stack counter. So this is what happens. This is what happens when you make a system call. You don't, in your programs, you don't directly call the system routines. You usually use some kind of a standard function like the read function. It is okay to you can directly call the system functions. It's okay, but usually we use some kind of a library function which makes the system call for us. Okay, so it seems kind of complicated, but it is not that much actually. It is not much different than calling another function. It is expensive though, because why it is expensive? Because when you trap to the kernel space, okay, you need to change the computer CPU's mode from the user mode to the kernel mode. Okay, that's one thing. After that, you need to save all of your states in your process, and after you save them, you start running another process, another program. So since these two spaces are different, switching from this space to this space and switching from this space to this space is kind of expensive. So it is as easy as calling a function, but in terms of CPU time, making a system call is expensive. That's why we don't call system routines so frequently. Otherwise, our programs will get slower and slower. Okay. Any questions on this? We will look at more details about this kind of mechanism between the user space and the kernel space. This is just an introduction. Okay.
Hocam o tabloya ne isim veriliyor? Oradaki tabloya ne isim veriliyor?
Dispatch table.
Evet.
Dispatch table.
Tamam.
It changes from system to system. It's just a lookup table. It's like the V table of the polymorphism, right? In the polymorphism, you had the virtual function table. This is the system function table, or system call handler table. And it doesn't have to be this way. This is just a conceptualization. Okay. So let's look at some of the possible system calls for some popular systems, like the Unix system. In Unix, we have this POSIX standard, right? What is POSIX? Portable operating system interface for Unix or something like that. So POSIX is a standard that specifies the interface for an operating system. So it's like an API for an operating system, right? It's like an API for an operating system. So POSIX specifies around 100 procedure calls. One of them is the read, the other one is write, and open the ones that are related to the files. And we do lots of other stuff too. We are going to look at some of those. Most of these calls you already know from the systems programming course. So I am not going to look at them in detail. Okay. By the way, not all POSIX procedure calls, okay, map to a system call. Sometimes it is handled in the user space. Okay, when you call one of these 100 procedure calls, that doesn't mean that you trap into the kernel space. Okay, sometimes you may handle everything in the user space. So each POSIX call doesn't mean that you are making a context switch. Sometimes you completely stay in the user space. It depends on the implementation of the operating system. Linux might do it differently. Some versions of Unix might do it differently. The important thing is that you should provide this functionality, this 100 procedure call, then you are an compatible operating system. Okay. Okay, so this is again the same thing that I was talking about. POSIX does not specify whether they are system calls, library calls, or something else. The important thing is that I should have this API. They should all be available. So let's look at some of the process management system calls. The first one is fork. We all know this. When you call fork, what does it do? It creates a child process identical to the parent. So the child process, it is identical to the parent. So at the end of fork, we have one more process, which is the child of the current process. But it is exactly the same as the current process. So how do we differentiate between the parent process and the child process when we call the fork? Because it is identical. Whatever PID is returned, it is going to tell me if it is a parent or if it's a child, right? So we look at the return PID number, process ID. In Unix, all the processes, they all have to have one unique ID, okay? And we refer to them by using this unique ID. That unique ID is obtained from this fork system call. Another call, wait PID, process ID. It waits for a child to terminate, okay? You give the child's process ID, and when the child terminates, it returns the status, and that status is stored in this variable. And there are some options, I don't know the details of these options now, okay? So if you have a child and you want that child to complete some task and you want to wait for it, then you call this one. If you don't want to be the same as your parent, remember fork creates a new process, but it is exactly the same as the parent. If you wanted to change your core image, you want to be another process different from your parent, then you execute this, you call this system routine exec VE with your environment variables and everything. It executes a system command or the Unix command in this process, and it completely changes the process's core image. It changes everything in the process. Okay, so this is if you want to execute something, a Unix command, you use this one, but it changes everything in you. There is no going back. Okay, and another system call is exit. When you call this exit, it is exactly the same as the C function exit. Okay, you provide a status number, and you exit. The system handles all the cleaning up of the cleaning up routines of the process termination. Okay, so these are some of the most important process management system calls defined by the POSIX. If you are writing an operating system, POSIX compatible operating system, you have to write each of these correctly. You have to write fork, you have to write VPID, you have to write exec VE, and you have to write exit. As I said, there are about 100 procedure calls. If you implement all of them, then you are a compatible, POSIX compatible operating system. If you keep some of them out, then you are not POSIX compatible. Okay, any questions on this? So I'm going to look at some of the other system call types, like the file management and what else? Okay, that's it, only the process management and the file management. But before going to the file management, the book provides a very nice C code that behaves like a shell, like a C shell or TC shell. It is much simpler though. It takes a command from the command line, okay? It executes it, and then it takes another command. This is what it does, okay? There's an infinite loop here, infinite loop. And this type prompt asks the user to enter a command, okay? You enter a command, you read that command, okay? You read that command and its parameters, like what might be that command. It is a Unix command. It might be it might be that command might be, the user might type ls minus t. What does this do? ls minus t. List the directory contents minus t. It sorts them by the time, the modification time. Okay. So when you say ls minus t, this one reads, okay, these two are written by yourself, okay, these are very simple functions. You read that command is ls and minus t is the parameter, then you call this function fork, okay? Fork makes a system call fork, and it creates a new process. And how do I differentiate myself with the, because it is exactly the same thing, it is exactly the same process running, copy of the same process, okay? So I need to differentiate between myself and then my children, my child. So what do? This is the parent code. If fork is not 0, that means that I am the parent. If fork is 0, it returns 0, then I am the child. If I am the parent, then I will wait until my child is done. Then I call this system routine wait process ID. If you say -1, okay, as the remember this is process ID. If you say -1, this means that you are going to wait for your child to finish, and I expect this status work, and I am not going to send any options. Okay, so this will block until the child is done. So what does the child is doing? Child is executing this. Child is executing this command with these parameters and no options. Okay, at the end of the loop, I go back top of the loop. Okay, so this continues in an infinite loop. It's like the shell. How do you stop the shell? You shut down your computer, right? That's how you stop your shell. Okay, this is a very simple loop-based implementation of a shell. It just makes two system calls, fork and three system calls, fork, wait, process ID, and execution of a command. Any questions? Yok bir soru.
Hocam gerek var mıydı fork yapmaya diyorsun hocam şimdi?
If we don't, so you are saying that just use this one.
Yes, sadece execute şeyini kullanarak satın.
Instead of just get the command and execute the command, so what would be the problem with that one? The question is, why do we fork? Instead of forking, just get the command and execute the command. And so what is the problem with this? We could be much more simpler. Okay, we could be simpler, much simpler. We didn't have to use fork and wait ID, but there is a very serious problem with this one. Yes.
Program might terminate before the exit command.
Yeah. But you just he says that do this. Exec VE command and parameters and 0 and don't write any of these. And I am in a loop. Read the command and execute it. Read the command and execute it. Why don't we do this? Yes?
Cannot do anything.
Cannot do anything?
We are waiting for execute stop for
When this is done, it will come back and you go to the top and do another thing, right?
Hocam normal 5 mantığıysa o
do same time.
The other one doesn't do it at the same time either. It does a single thing at the same time. Just a single thing. It doesn't do things in parallel. Yes.
Hocam child'ın sağlıklı bir şekilde hani diğer işlemlerin bloklanarak o exe'yi yapması için değil mi? Hani wait PI'de bekliyor ya, blokluyor diğer işlemleri.
Çünkü iki tane proses var. Bir tanesi öbürünün bitmesini bekliyor ki bir tane bitmez yenisini başlatacak.
hocam
Child'ın işlemini yapması için exe'yi diğerlerini blokluyor ki o yapsın hocam. Yani bu da amacı değil mi?
Diğerlerini de blokluyor.
Hani wait PI'de beklerken.
Wait geldi kendisini blokluyor. Bekliyor child'ın bitmesini. Arkadaş diyor ki child niye yapıyorsun? Kendisi yapsın şimdi. Niye child'e yaptırıyor diyor. Evet.
Hocam 5 mantığında şey var. Şimdi o child proses o işlemi tamamladıktan sonra kendisi ölüyor. Eğer biz parent prosese yaptırsaydık parent proses ölecekti. O şey devam etmeyecekti diye tahmin ediyorum.
Neydi execV'nin tanımı? Şunun. Replaces the process's core image. ExecV'yi çağırdığın zaman sanki bir prosedür çağırması gibi git şu komutu çalıştır gel demek değil o. Sen artık bu komutsun demek. ExecV'nin manası o. Onu çağırdığın zaman kendi core image'ini yeni komutla değiştiriyor. Artık ls-t oldu o. Tamam mı? Geri dönme diye bir şey yok. Artık o. Dolayısıyla execV'yi çalıştırırsam ben eğer burada şu while loop'u falan filan kalmıyor ortalıkta. Sadece bu proses LS'i çalıştıran bir prose dönüşüyor. Geri dönme diye bir şey yok. Geri dönme diye bir şey yok. Adamlar öyle tasarlamışlar bunu. Fork bir tane proses yapıyor. Bir şeyin tıpatıp babasının aynısı. Bu ama şu verilen Unix komutunu çalıştıran bir tane prosese dönüşüyor. Onu çağırıp geri gelmiyor, tamam mı? Öyle bir şey yok. Bir tane yeni bir proses çalıştır, onu bitince de geri gel diye bir şey yok şeyde Unix'te. Ya bir tane kendine tıpatıp aynısını yapacaksın, tamam aynısını olacaksın ya da benim prosesimi tamam bitti, ben artık şu proses olacağım diyorsun. Yeni bir tane proses başlıyor, o bu. Benim kopyamı yap bu. Tamam, ben başka bir şey olmak istiyorum diyen de bu. Başka bir şey olduktan sonra tekrar geri dönmek yok. O yüzden bu çalışmaz. Yani çalışır da bir defa çalışır. Bir tane komut alır, onu çalıştırır. Ondan sonra da o komut en sonunda ne yapıyorsa o kalır geriye.
Thread'de falan yapılsaydı hocam nasıl olurdu? Yani o mantık yine işte.
Thread'den daha kuvvetli bu proses yapıyor.
Evet işte çok şey kaynak tüketmemek için thread yapılsa yine thread olur.
Hayır yok, thread güzel bir fikir değil. Ya, threadler hakkında çok konuşmadık ama thread bir defa aynı prosesin içerisinde, tamam mı? Aynı prosesin içerisinde stack, ondan sonra heap, environment variable gibi bazı kaynaklarda ortak kullanan başka bir execution aynı prosesin içerisinde. Ben yeni bir command execute ederken aynı prosesin içerisinde kalmak istemeyebilirim. Onun kendine göre environment variable'lar olacak. Onun kendine göre stack'li olacak. Benimle bir şeyi paylaşmak zorunda değil o. Thread sınırlayıcı bir şey. Hızlı ama sınırlayıcı bir şey. Burada yeni proses yapmak istiyorum. Okay, if there are no questions, let's move on. Let's look at these file management system calls. We all know this, right? Open, close, read, write, lseek, and the status. These are all C functions. These are all C functions, not due to coincidence. These are all C functions because C functions in turn call the POSIX system routines. So they are library routines again. You call the C function, and the C function makes a system call. Okay, so they are very easy functions to implement these. Open, close, read, write. But underneath, inside the operating system, complicated stuff happens, and that's beyond us. We don't care how complicated they are. They are just operating system calls, and we just use them. Okay. So we know what those are. We already talked about this read function, and the rest of them works in a similar way. What else? Again, file management, making directories, removing directories, linking, unlinking, mounting, unmounting. What is a link? Where do we use this system command link? The system routine link. You know link, right? You use command link. Niye konuşmuyorsunuz ya? Evet.
Çok kullanılan komutları, bazen grep'le falan bir komut kullanırız mesela terminalde. Onu kısa bir yöntemle, kısa bir kelimeyle link yaparız. Sürekli mesela AA gibi çağırırız.
Yani kullanma nedenlerimizden bir tanesi o. O sanki çok uzun isim olan bir tane komuta kısa bir isim vermek için kullanabiliriz diyor arkadaş.
Ya da çok kullandığımız hani sürekli.
Evet. O linkli yapabilirsin ama onu yapmanın başka yolları da var. Shell'de de oradan alias'la yapabilirsiniz. Yani. ile de link yapmana gerek yok. Link bir dosyaya başka bir isim vermek, arkadaşın söylediği gibi. Bir dosyaya başka bir isim vermek, komut olmak zorunda değil. Başka şey de olabilir o. Ya da nasıl şöyle bir şey yapabilirsiniz. Bir dosyanız var 20 GB boyutunda. O dosyayı başka bir yere kopyalamak yerine başka bir yere onun linkini alıyorsunuz. Aynı yeri gösteriyor ikisi de birden. A dosyasındaysanız B dosyasında da birbirine linkse onlar. Aynı dosya açılıyor ama farklı yerde yaşıyormuş gibi duruyorlar. Farklı yerde yaşıyormuş gibi duruyorlar. Mesela bu sınıfta herkesin bir tane hesabı olsaydı Unix makinesi içerisinde, ben de size bir tane işte 20 MB boyunda bir tane video versem, herkes o videoyu kendi direktörüne kopyalamak yerine kendi direktörüne linkini alsa sadece bir 20 MB'lık dosya kullanacak ama 100 kişi o dosyayı kullanıyor olacak. Farklı farklı isimlerle herkes kendi gibi kafasına göre isim verir. Mount ne işe yarıyor? Mount.
Sistem
İmai dosyada ama
Nerede kullanıyorsun Mount'u? Ya bunlar niye bilmiyorsun? Sistemler sağlanan siz.
Taktığımız zaman
Sen ne diyor Erkan Hoca? Sınıfta 200 kişi var ama diyor 180'i gelmiyor diyor. Yok diyor. Hiç uğramıyorlar diyor. Geçmeye niyetleri de yok diyor. Orada bunların hepsi birer birer anlatıyor güzel ya.
Hocam
İşte bunda var en azından. Anlatmıyorsa anlatmıyor falan. Ne işe yarıyor ama?
hard diski, mouse, USB falan sisteme tanıtmak için.
Evet, yeni bir device'ı kendi file sistemime monte ediyorum. Öyle düşünebilirsin. Yeni bir device'ı kendi file sistemime monte ediyorum. Böylelikle artık ona doğrudan directory structure içerisinde erişebilirim. Unlink ile unmount da bunların terslerini yapıyor. Birazdan onlara biraz daha dikkatli bakacağız. Link and mount'a. Okay, these are the other stuff. Changing directories, changing mode, kill sends a signal to the process. You specify the process ID and you specify the signal type. Okay. For example, signal number 9 is for terminating the process. If you send the signal, okay, if you send this signal to a process, that process will be killed by the operating system if that process doesn't know how to handle that signal. Okay. If you want to communicate with the process using the signals with numbers, sending numbers, then you can use this. System call. Okay, and we have time. We get the elapsed time since January 1st, 1970, in terms of seconds. We will talk about this in a little bit later. So, we will see more details about this, but as an introductory material, let's look at the memory layout of a process. Okay, in a process, I have my address space from a small number to a large number. In this case, the largest number is very small, but it's a larger number than this. So at the bottom of the address space, I have my program text, and on top of that, I have my global data and the dynamically allocated data. So when I use malloc or new operator, I get space from this heap. And at the top of my address space, I have my stack. Okay, so stack grows downwards. Okay, stack grows downwards. If the stack grows until this point, then I have stack overflow. Okay, so there is a pointer for this position. There is a pointer for this position. This position is called stack pointer. It's a special register. Okay, when you make a function call, remember how do we make the function calls? We put our parameters, we put our parameters, and we put our local variables into the stack. We push them onto the stack. Okay, and stack grows downwards. And when we allocate new stuff comes from this part of the process. So each process has a space like that. Okay, if I am process number 1, P1, I have a structure like that, and if I am process number 2, I have exactly the same structure like that, okay? So the address is 0, 0, 0, and F, F, F, F. And I have to keep these two processes on my memory at the same time, okay? I have to keep them in my memory at the same time. How many processes I have? 60, 50, 100, I don't know. So all of them has to see the process address space like that. So it is the responsibility of the operating system to show the address space and the program address space like this for all the processes. So in fact, there is no address space in physical addresses. There is no address space like that on the computer or the memory. Operating system, with the help of the hardware, makes it look like all the processes have their own address space like that. Okay. So we will see the details of this when we look at the details of processes and the memory abstraction. Okay, any questions on this? So this is how the Unix system works. The other systems have similar structure, similar abstractions. There might be slight variations. Let's talk about this linking. Okay, when I say this link, okay, when I say this user gym memo user AST node, I am linking from this location to this location. In Unix, every file has a unique ID. Like every process has a unique ID, process ID. Okay, every file has a unique ID which is called inode, inumber. Okay, inumber is the unique number for each file in Unix. That includes the directories. Okay, directory is a special file, yet it is still a file, and all the files, including directories, they have their I numbers. Okay, I said that directory is a special file. What kind of special file? In a directory, you have a list of files and their I numbers. For example, this is the user ASD directory. Okay, it has 3 files: mail, games, and test. These are the I numbers. Okay, so the 16 is the I number for mail, 81 is for the games, and 40 for the test. How about user gem? This is another directory. It has 1, 2, 3, 4 files and their I number. So when I execute this system call, link, okay, link user gym memo and user ASD node. Let's see the difference between those. So what happened? I have one more file in my directory user ASD. Its name is node, but see this number and this number is the same. So this node is linked to memo. Node is linked to memo because their I numbers are the same. They are actually the same file. Their names are different. If I open memo from this directory, I will see the contents of node. If I make a change inside the file of node, memo will be changed automatically because they are the same thing. They are linked together. It's like an alias, like a name. If I remove node, memo will stay there. If I remove memo, node will stay there. It will not be removed. If I remove both of them, then this number 70 will disappear because I don't have a I number 70 anymore. Both of them have to be removed. Yes.
Hocam hard link yapma şey var mı? Hard link yapabiliyor muyum?
There are various options about linking. We will talk about them when we talk about file systems. There are various versions of linking, soft linking, hard linking, and we will discuss about their implementation and their effects later. Okay, so this is called linking. This is called linking, and it's very useful most of the time. We use linking with this mounting stuff actually, and this is what happens when I mount. This means that I am mounting my USB drive 0 to this position, /mnt. /mnt is here. After I execute this system call, this is what I get. Okay, this is my USB disk mounted on this position. Okay, this is my USB disk mounted on this position. Now, if I wanted to access to this directory, all I need to do is go to this directory mnt, then from this directory go to this directory. Let's say this is still mnt, mnt. Let's say this is abc. What do? I say cd/mnt/abc. Now, using this command, I can go inspect my file contents inside my USB device. Sometimes I do this. Let's say I mounted my USB drive to this position. If I, after mounting it, if I make a link from this mount point to my home directory, it would look like I have a new directory in my home directory, but it's not actually. It is mounted from a USB drive. So it is very transparent for the user. The user thinks that it has new data in his new directory, but that new data is coming from a USB drive or a hard drive. Okay. So without the users noticing anything, you can do lots of linking, unlinking, and mounting to make the system more efficient. Okay, so this is called linking and this is called mounting, and they are related to each other. I don't know what this is, but okay. I guess this was about time. Remember this time system call? The time system call returns the number of seconds from this point, January 1st, 1970. January 1st, 1970. Okay, so it returns it in terms of seconds. How many seconds pass? But it has to return some kind of an integer, right? For a 32-bit system, the maximum integer, unsigned integer, you can keep as this much, right? 2 to the power 32 minus 1. So it makes, so this is the largest number of seconds that it can return. So if you calculate the years for this second, it makes 136 years. So that means that before 2100 or something, in 100 years, I don't know, I guess in more than 100 years, these kind of systems will be in big trouble. 32-bit Unix systems. But I don't think that we are going to have those kind of systems in 100 years. You need to switch to 64-bit system in 100 years, otherwise you will be in trouble. Okay, what else? Windows, okay, this was the POSIX system calls, POSIX compatible system calls. How about Windows? Okay, Windows specifies an API. Okay, it doesn't specify procedure calls. It specifies an API, like a library API, and each API call doesn't have to make a system call. Okay, sometimes that call is handled in the user space. Sometimes it is handled in the kernel space, and it changes from version to version. If let's say this one, let's say create process, not maybe this one, but let's say this one, read file. Let's say I made this call read file using the API in Windows, okay, read file. In Windows 8, it might mean that I need to make a system call, but in Windows 10, it may not make a system call. So it is up to the implementation of the API, which is implemented by the Microsoft. Nobody else is implementing this API. Nobody seriously is implementing this API. So Microsoft has the flexibility of handling the system call inside the kernel mode or the user mode. But it always provides an implementation for these API functions. It's a little bit different. So there is a nice comparison between Unix and the Windows API. For the Unix, we have fork to make a new process. In Windows, we have create process. It creates a new process. Okay. For the wait process ID, we have wait for single object. Okay. We have no corresponding API function for execve. Okay. So instead of using this one, we use create process. Create process forks, creates a new process and executes a command. So it does both of them at the same time, create process. Okay. So there is no exactly the same thing as the fork function in Windows. And we have open, close, read, write, seek, status, making directories. There is no directly supporting link from the operating system. There are links in Windows, but it is not directly supported by the operating system kernel. And for unlink, I have delete file. Mounting, unmounting, we don't have it. In Windows, in the kernel mode, we don't have user permissions for the changing mode. Okay? And we don't have signals in Windows, and we have the local time, not the seconds since 1970, but we get the current time. So I can calculate the difference between the current time and the 1970. So these are some comparisons between POSIX system calls and the Windows API. There's another difference between POSIX calls and the Windows calls. The number of how many procedure calls, how many system calls in the POSIX? How many? Around 100, right? For Windows API, we have thousands. There are many API calls, and most of them are related to the windowing, okay? Graphical user interface. In POSIX doesn't specify about the graphical interface. It doesn't specify anything about the graphical user interface. All the graphical user interface is done in the user space. Okay, it is done in the user space, not in the kernel space. But for Windows it is done in the kernel space. That's why it is a little bit more efficient to deal with the Windows windowing interfaces with the Windows, because running in the kernel mode is more efficient. You don't have to make calls to the kernel all the time because you are already in the kernel. You have direct access to the hardware when you are in the kernel mode. In Unix, we don't do that. You need to make system calls all the time to access the hardware. So for the Windows, it is a little bit more efficient to have a graphical user interface. Again, but that comes with the cost of crashing your system. When your Windows crashes, when your graphical user interface crashes in Windows, okay, whole system crashes. But with Unix, when your graphical user interface crashes, only the interface crashes. Your system is alive. You can rerun your graphical user interface, whatever it is, and you can continue your work. That's the upside. There is a downside and there is an upside. Downside is Unix is a little less efficient. Upside is it is robust against the crashes related to the graphical user interface. Okay? Any questions? Bu başınıza geldi değil mi? Her şeyde Windows, Unix'te Linux kullanırken pencerelerle ilgili bir problem çıkarsa mouse çalışmıyor falan bir şeyler olmuyor. Crash olmuş, hiçbir şeyle etkileşemiyorsun ama sistem hala arkada çalışıyor. Nasıl erişiyorsun sisteme? Bir şekilde işte terminal açıyorsun, siyah terminal. Oradan bakıyorsun hangi pozisyon olmuş. İcabında gidip pencereyi olduğu gibi işte GNOME ya da KDE'yi öldürüyorsun. Tekrar başlatıyorsun bunları StartX'le falan tür şeylerle. Windows'da yok. Windows'da çünkü pencereler doğrudan işletim sisteminin parçası. Pencereyle ilgili bir problem çıktığı zaman, crash olduğu zaman tüm işletim sistemi göçüyor. Nadir olan şeyler. Eskisi kadar sık olmuyor. Eskiden çok daha fazla olurdu. Okay, so that was that was the introductory stuff we discussed about the operating system. That's because some of the structures available for the operating systems. How much time do I have? I don't have any time. Let me show you this a little bit, and we will stop in 5 minutes. The most common computer operating system organization is the monolithic approach. Monolithic approach. What do I mean by monolithic approach? A monolithic approach, the entire operating system runs as a single program in kernel mode. You have a single process, okay, single program, and it is operating system, okay. Inside this single program, everybody can call everybody, okay. When I make a procedure call, let's say read can call write can call fork can call others. There is no restriction. Everybody can call everybody, so it is very, very efficient, very, very flexible to write these kind of systems. But the problem is, a crash in any of these procedures will take down the entire operating system. If you have a buggy part of the operating system, that will affect the whole operating system. So if you make your complete operating system a single program in the kernel mode, it is efficient to run for the small systems. It is easy to write maybe, but understanding is difficult, debugging is difficult. Also we have these kind of problems. That's why people didn't like those kind of monolithic systems. They wanted to have some kind of a structure to it. In this structure there is an entry point. In this entry point, okay, it's like make a system call. After you make the system call, there is a dispatcher. It decides which call is going to make, service procedures. And those service procedures can call those utility procedures. So they are not allowed to call this one, cannot call this one cannot call this one. There is only a few utility procedures available for each of those service procedures. So this is more structural, more restrictive in terms of designing the operating system and writing the operating system. It takes more time to design it and think about it. But again, if there is a problem with one of these utility procedures, it only affects this service. All the other services, they can stay alive and they can still work. In the other one, everybody calls everybody. In the other one, the structure is like this. Everybody is connected to everybody. Okay. So if this one fails, it will make all the other procedures potentially. So the monolithic operating systems are easy to write, efficient to run, but they have these kind of problems. So what else they did? They said that okay, let's do this layered system. Layered system, it is similar to this one. There are layers in the operating system. For example, this is an example from the operating system. The operating system. At the bottom of the layers, there is process allocation and multi-programming. On top of it, there is memory, RAM, and memory and disk management. Okay. Then operator process communication, input-output management. It goes like that. And at the top, I have the operator. So when there is a procedure operating system call, it has to go this way. Okay. So you make a call to the input-output. Input-output makes a call to the operator process communication, then the memory, and then the process allocation. With this layered architecture, it is easy to understand the operating system. It is easier to write or design the operating system, and it is easier to debug the problems. If there is a problem with the memory, I know that it is in this layer, and it will not affect the problem. It will not affect anything in the layer number 0, which is the most important layer. Okay. If there is a problem here, I can still have my processes running because I don't have any problem with the process multi-programming. Okay. If there is a problem there, input-output management, again, I don't have any problems here. So the layered architecture is used. Remember that operating system Multics has the same structure. Instead of layers, they have rings. At the center of the operating system, there is a kernel. Then I have rings like that. Okay. It is like a layer system, but they call it rings. And this is the most important part of the operating system. Very small but most critical. Then it goes like that, and at the outer end of the operating system, I have the user space, users, like that one, user programs and the operator. And this operating system, the operating system, design the operating system according to this structure, but Multics, it designed it according to this structure and it runs it according to this structure. So when you run your operating system, there are rings and you have your ring numbers and everything. So Multics is maybe the first serious system to implement such a structured operating system.
What's the difference between the layer structure and the ring structure?
It's just a naming convention, that is the difference.
Just it?
Yes.
Can the user program can access the layer below and the layer
No,
below it?
you just communicate with the layer before you, and so the communication is like this way. By the way, the users can create their own rings in Multics. There's a very good example in the book. If you are a professor, you have your ring, and your students have a ring above you, and your students cannot access your data, but you can access your students' data using this ring structure. This layered structure did not implement everything in the practical implementation, but this one I will implement it in Multics in 1965. Any other questions?
No, I don't. But
Because if you don't
you
ask
guys
any-
outside has
Because-
some questions. When you are going to leave.
Okay, so if there are no questions, that's it for today.